All right, let's get right into it. How do you launch a fighter jet off an aircraft carrier in just 2 seconds? I mean, we're talking about one of the most incredible, most extreme feats of engineering you can imagine. You've got this massive, multi-ton jet on a floating runway, and you have to get it airborne in literally the time it takes to snap your fingers. It's just this wild mix of raw power, hard physics, and pinpoint precision. And that's the core of the problem, right? Think about it. A 30-ton jet. We're talking loaded up with fuel, loaded up with weapons. It needs a ton of runway to get up to speed and fly. But on a carrier, you just don't have that luxury. Not even close. So you have to ask, how on earth is this even possible? So let's really put this into perspective. A normal runway, on land, you're looking at around 2,500 meters. Plenty of room. But on a carrier deck, you've got maybe 300 meters, and that's for everything. Taking off, landing, parking the other jets. The space you have to work with is just tiny in comparison. The scale of this engineering challenge is just immense.
Okay, so this is where the real problem starts. It's all about the physics. To solve this puzzle, engineers couldn't just change the plane, and they definitely couldn't change the laws of lift. Nope. They had to invent a machine, something that could basically bend the rules of acceleration.
And here's the first number you need to wrap your head around. About 150 miles per hour. That's the magic speed. To get enough lift to actually fly, a fighter jet has to hit that speed. It's totally non-negotiable. And get this, it has to go from 0 to 150 miles per hour in about 2 seconds. I mean, just think about that for a moment. That is such a violent, incredible acceleration. No supercar on the planet even comes close. So what does that feel like for the pilot? Well, during that launch, they get slammed back into their seat by almost 3 Gs. That's 3 times the normal force of gravity. It's basically a controlled explosion, and they're sitting right on the tip of it. Okay, so we've got the problem. How did they solve it for, the last 60-plus years? The answer was pretty much brute force. Pure, raw power, coming from the very heart of the ship, steam. This was the classic solution, the technology that basically defined naval aviation for decades. And honestly, the easiest way to picture this is to imagine a giant high-pressure steam piston. Seriously, deep below the flight deck, there's this massive system of cylinders. It's kind of like a giant potato gun, except, instead of a potato, it's flinging a multi-million-dollar fighter jet into the sky. So let's walk through how this whole mechanical ballet works. First, they hook the jet's front wheel, the nose gear, into this little cart called the shuttle that sits in a track on the deck. Down below, steam from the ship's reactor is building up to this insane pressure, around 520 psi. Then, when it's time to go, a holdback bar breaks loose. All that steam expands violently, just shoving a massive piston forward at an unbelievable speed. That piston is connected to the shuttle, which yanks the jet down the track and literally throws it into the air. It's just such a raw, powerful process.
But here's the thing about steam. For all its raw power, it was really rough on the airplanes. It was mechanically stressful, it was hard to control precisely. So for the modern era, for the newest carriers like the USS Gerald R. Ford, engineers look to something that sounds like it's straight out of sci-fi, electromagnets.
Yeah, the system is called EMALS, which stands for Electromagnetic Aircraft Launch System. And instead of that big steam piston, it's essentially a giant linear electric motor. A huge surge of electricity creates this powerful moving magnetic field that just zips the shuttle and the attached aircraft down the track. It's less like a steam-powered catapult and way more like a giant railgun. And the amount of energy we're talking about here is just staggering. I mean, every single launch uses enough electricity to power a small town for a little while. All of that energy has to be stored up and then released with absolute, perfect control every single time. And this is exactly why EMALS is such a game changer. The acceleration is still incredibly powerful, but it's much smoother, which means less wear and tear on the planes. It's also super precise. You can tune it perfectly to launch anything from a heavy, fully loaded fighter jet all the way down to a much lighter drone. Plus, it has fewer moving parts, so maintenance is easier, and it can reset for the next launch in about 45 seconds. That's a huge deal for efficiency. But, all this amazing tech, whether it's steam or electromagnets, is completely useless without the people. The flight deck of an aircraft carrier is, without a doubt, one of the most dangerous and complicated workplaces on the entire planet. Every single launch depends on a team of people working in perfect sync. And to keep all this chaos organized, the crew wears different colored shirts. It's like a color-coded system. The folks in yellow,
They're the aircraft directors, basically the traffic cops of the flight deck. The green shirts are the ones operating the catapults. Purple is for the fuel crew. They're called grapes. And the red shirts are the ones handling all the weapons. It's this incredible, carefully choreographed human dance.
And of course, the story doesn't end with EMALS. Not at all. Engineers are always looking to what's next. They're already designing the launch systems for the next generation of aircraft. Planes that are going to be even faster, way smarter, and sometimes not even have a pilot on board.
So what does that look like? Well, we're talking about things like magnetic superconducting catapults for way better efficiency. We're talking about advanced systems just for launching drones. And then there's the really big one, figuring out how to launch hypersonic aircraft, vehicles that can fly at more than 5 times the speed of sound. That's a whole new level of challenge.
And that really brings us to the big question, doesn't it? We've gone from these brute force steam pistons to what are basically electromagnetic railguns. Carrier launch tech has always pushed the absolute limits of engineering. So as we get into this new age of autonomous jets and hypersonic flight, what's the next great leap going to be? What will that next revolutionary system even look like?